Okay, welcome everybody. Hopefully, there's no audio issues with my mic. I had to change a bunch of stuff. I went to plug in the document camera yesterday, and the port, the video port on it, basically imploded, fell into the camera. I could hear it rattling around inside the camera, so I had to immediately go to campus and get a replacement. Which hopefully, yeah, not hopefully, it was definitely easy to do. So everything should be working out a lot better now. So anyway, yeah, to compensate for that, the lectures this week will be like 20-ish minutes longer than normal, and then we'll be back next week to the normal 11 to 12, 20-ish lectures. So anyway, welcome to the course. I posted it in the syllabus, but this is the textbook. So there it is. We'll be following the textbook pretty closely. And as I mentioned, even though combinatorics comes first here, we're going to be starting with graph theory. The textbook and the course is designed that we could start in either order. It doesn't matter whether we start with graph theory or combinatorics, but we're going to start with graph theory. That's the contents of chapter 1 in the textbook. We'll be going through most of the contents of chapter 1, and then most of the contents of chapter 2 as well. That's the combinatoric stuff, and then some topics selected from chapter 3 as time permits. So we'll also, depending, before we get to chapter 3, we might take some topics from other places as well. But anyway, that's the general plan. And the overall goal of the course is it's going to seem like kind of a shotgun approach of there's going to be a lot of definitions, lots of terminology thrown your way in kind of a fast fashion. A lot of you have probably seen graphs in some context before, so some of it's going to be familiar, but it's going to be a lot of terminology sent your way, and it might feel a little bit overwhelming, especially on a summer schedule because we're doing this every single day. But unfortunately, that's just how it's got to be. So anyway, the goal is that by the end of the course, you'll have pretty good introductory understanding to both combinatorics and graph theory, and then be able to delve a little deeper into either of those topics as you are interested or as you need to. As you need to apply it for whatever it is you're interested in thinking about. So anyway, that's the deal. So little introduction here, since we're starting with graph theory. Depending on who you talk to, you could say that the following problem I'm going to list is either the beginning of graph theory. It's almost certainly the beginning of graph theory, but some would say it's also the beginning of topology, which is also true. This is the bridge of Königsberg problem. So bridges of Königsberg. Maybe you've heard of this problem before. This was investigated by, well, it was settled by Euler. In the city of Königsberg at the time, there were bridges connecting some land masses in the city. Roughly, this was the arrangement of those bridges. So here's water, and the bridges were here, 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 and here, and I believe there were two other bridges connecting these two land masses. Okay. Now, immediately, if you know anything about graphs, you might see how this translates into a problem on graphs. But what was the problem? The problem was crossing each bridge exactly once, traversing all the bridges, but only once, right? So that this was the problem. So no backtracking. The problem was traversing each bridge exactly once. Supposedly, the inhabitants of the city would actually attempt to do this or try to figure out a path or a trail that could do this, and they didn't succeed. Euler said this is impossible, so Euler was the first to really mathematically settle why this wasn't possible. So the question is why. You might already know why, but we're going to return to this in another context once we got some terminology and definitions under our belt and really see why. But this Euler posing this problem mathematically and solving it like this, he even says in the paper in which he did this, he said that the math hadn't really considered problems like this, didn't really have the same sorts of computation at its in its utility belt to deal with this, so you had to consider it another way. This is, a lot of people take this as being the beginnings of either, you want to say, graph theory or topology. Both of those work. But anyway, this was kind of like laying the groundwork. And there are many similar sorts of problems that are easy to state, easy to visualize and draw, that require a sort of mathematical analysis that's a little different than you might see in a course involving differential equations or something like that. So so this was kind of the very early beginnings of this stuff. Of course, this would explode much later, and of course continues to explode once you have access to computation machines that are more convenient to use. But anyway, this is like the very beginnings. So before we reformulate this in terms of graph theory and see why, one, this belongs to graph theory, and two, why graph theory can answer a question like this, I'm going to define what a graph is in the first place. So what is a graph? So a graph G. Depending on your mathematical background, you may have seen something like this before. When I say something like this, I mean the notion of a mathematical structure. So, for instance, maybe you've had an upper level algebra course, so you know what a group is, or maybe you've heard of a mathematical group or ring or field or something like that. And what that thing is a set and then a structure on that set. So in the case of a group, it is a set, and then it is a binary operation that satisfies certain properties that make the thing a group. Same is true for ring and field, although you have multiple binary operations in those cases. But a graph G is, well, it's two sets. So a graph G consists of two sets. And I'm going to go ahead and insert something here. We are going to start out talking about, well, we're going to start out talking about a restricted class of graphs. It's going to be most of our focus. So automatically, the fact that I say two sets, you have a quick question you can ask. You could say, are the sets, what kind of sets, right? Are they finite or infinite sets? That might be the basic question that you have. So for us right now, we are going to say two finite sets, although I'm going to list as a possibility if these are infinite. These consist of two finite sets. So the two sets are V, the set of vertices. So there's not a lot of structure on a set itself. We're not going to go into the mathematical logic direction necessarily. It's just a set. The objects in this set are vertices, right? Maybe I've labeled those with numbers. Maybe I've labeled those with letters from some alphabet, but those are my vertices. And then the second set are edges. The objects in the second set are unordered pairs of vertices. Okay, so this is exactly what a graph is. So for instance, because we are going to be drawing a lot of these in the course, because while of course I can list these out as sets as I am about to do for this example, they have a very natural and intuitive graphical representation, no pun intended here, that allows us to easily see what it is that's going on, and this is kind of the preferred thing. Now, of course, finite can still mean very huge, right? Like, just because you say finite doesn't mean it's small. Most of the examples to aid our understanding are going to be small. They're not going to be that many vertices, just to make it easy for us to draw these things. But of course, saying finite here, right? Like these graphs could still be absolutely gigantic. Of course, you might have already thought about that. So here, I'm going to label these A, B, C, D. And we'll do this. All right. Okay, I just kind of picked those randomly. And so here, for this graph, if this is my graph G, looks like this. My set of vertices, this would be the set consisting of these things I've labeled A, B, C, and D. And my edges are going to, the way that I've drawn them in, not every possible edge that could exist does in this graph, as you see here. So I look and see, okay, I have AB, that's a pair. They are connected by edge. That is the edge that connects them, so AB. I have BD, no particular order here. I have BC. What else do I have here? What did I miss? I missed AD. Now, here's the thing. You can see here that this is going to be extremely unwieldy and not so great in terms of conveniently labeling these things. So we're not going to typically be labeling things like this. And in fact, when we do label the edges, we're going to have a better way of writing those. But for now, this is just showing exactly how this works. So there's not a whole lot of structure on a graph, right? And I should stress that even though, of course, I drew A, B, C, D roughly in a square, the graph absolutely does not refer to my vertices being arranged in any particular way, right? I could have drawn this graph. I could have drawn this graph like this instead, right? I could have put all of the vertices like this. And so long as I had drawn the lines in a way, so here, let's in fact just do this, right? So here's A, B, C, and D. I have the edge AB. I have BD. I'm going to draw it like this. I have BC. I'm going to draw it like that. And I have AD. Okay, so here is my graph G. We don't, of course, have the terminology yet for talking about how these two graphs compare to one another, but we will see that these are the same graph. Okay. Of course, I could have labeled these instead of A, B, C, D. I could have labeled them 1, 2, 3, 4. And the question is, are those the same graph? Yes. And again, we're going to have terminology for dealing with that. But all of this, all of this will come. So first, the main thing I just wanted to stress was that it didn't matter where these vertices are, and it doesn't matter how the edges are there. The point is that they're just sets. Whatever way you come up with representing those things, as long as you are not being ambiguous here, this is fine. You might choose something like this, like arranging them as vertices in a regular n-gon, right? Just because that's convenient. It's a convenient way of organizing things, right? Like if you treat your vertices as being on a convex, regular polygon, that's a very convenient thing, but it's not necessary, of course. But like I said, you might find yourself doing that anyway. Okay, so let us discuss some other things. So because there's not a whole lot of structure here, right? It's literally two finite sets right now, vertices and edges, and the edges consist of unordered pairs of vertices. So naturally you ask yourself, like, what happens when I change this just a little bit? So for instance, what if I take the edges and instead of insisting on them being just unordered pairs of vertices where there's no direction here, right? It doesn't matter. Instead, I add the stipulation that these be ordered pairs, where the order does matter. I am tracking the order in some way, right? So very first thing I could do, so what if the edges E consist of ordered pairs of vertices? So I'm just going to draw, again, a quick picture here. So here, maybe I'll even add this over here. So when I draw an edge, so if I've labeled these, we'll say these are A, B, C, D, E. Okay, so my vertices consists of A, B, C, D, and E, and my edges then are going to consist of ordered pairs. So I'm going to draw in some ordered pairs here. I'm going to draw in, let's, but this is just a normal graph. When I draw in the edge, AB, I am putting an ordering on this, and we will say the convention here is that this is from A to B, meaning that I'm tracking the order. And in order to actually do that, what I will say is that I'm going to put an arrow that indicates this is from A to B, so that the edge here is tracked here as from A to B. I'm going to put a little arrow indicating that. All right, I'm going to do that with the rest of the edges here, so I'm just going to do this sort of thing. Right. So these arrows are each indicating that, so here, for instance, it indicates that the edge here is the edge EA, because it's going from E to A. And the edge here is BD. And so on. Okay. So you've changed your ordered or your unordered pairs to ordered pairs. So now that you are actually tracking this, how does this change the graph? Well, now these are tracked. This is known as a directed graph or digraph. Which you may have encountered before. There are applications for which maybe this is the object you're interested in rather than just a graph. Or maybe not, maybe you don't care. All right, so anyway, this is just one other sort of graph. What else can we change? What if my set E of edges can contain repetitions? So a set that can contain repetitions of elements is called a multiset. So what if So my headset powered off because again, new um, setup. So I'm after this lecture, I'm gonna have to download the app for my headset and make sure to turn off that feature because of course there's no sound coming through because I'm lecturing. There's no sound coming through. It's doing the auto power save thing. So I'm sorry about that if it announces to me when it does this, so I'll be able to handle it this lecture. But if for whatever reason you see that there are giant blocks where I'm not talking, if you're in chat, please let me know if you don't hear something. So sorry about that. It's tech woes, but like I said, I'll fix it before tomorrow's lecture. So so what are the elements of E contain repetitions? I.e., what if E is a multiset? Multisets allow for repetitions. What would that look like in the graphs? I'm not going to label these graphs. I'm not going to go through that process. I'm going to draw, we'll draw graph like this. So here, between these two edges, there's one. We'll say that this edge repeats 3 times. All right. And then maybe this edge only repeats once, and then maybe we have these edges. This edge repeats twice in E, and then maybe, yeah, something like that. So I have 5 vertices here. Between these two vertices, there's a repeating edge 3 times. Between these two vertices, there's a repeating edge twice. What is that? Well, not being too creative here with name, this is multigraph. Okay. Again, there are reasons for why you would want to consider a multigraph. There are applications you might think of. We're not going to be concerned with this so much in this text, but this is definitely a property that you could put on a graph and then ask questions about. Furthermore, what if I allowed edges to consist of pairs of vertices, but the vertices don't need to be distinct, right? So what if an edge was allowed to connect a vertex to itself? All right, so what if an edge of E was allowed to connect a vertex to itself? Well, I mean, you might have something like this. So maybe you have something like this. Maybe these aren't even connected, but they could be. Right? So maybe throw that in just for good measure. So here are our vertices. Right? There's our vertices. We look at this thing, these loops, right? So here we have loops. It's obvious why we call them loops, because when you are actually putting down a visual representation of these things, how else are you going to draw them, right? This is certainly an intuitive way of doing that. Gives rise to these loops like this. What is this? If this sort of thing is allowed, this is called a pseudograph. Again, we're not typically going to be concerning ourselves with these in this course or in this textbook, but this is something at least to be aware of. It's also useful just to help hone your intuition for what it is you're talking about, what sort of thing is allowed, and when you draw a picture, making sure that you understand what is actually being referred to here. Okay. So, more talking about things we're not going to talk about. What if the edges don't have to be pairs? What if they're just subsets of vertices? Right. So what if they're not only pairs, but subsets of vertices? So now you might, first thing you ask here is like, how would you even draw this, right? What is this? How would this look? Well, the idea is maybe here are your vertices, and now your edges are subsets of vertices, so it doesn't have to just be two. When it's just two, you can draw some kind of curve or line between them. But say maybe your first edge consists of all three of those, right? You call that edge like E1. And maybe another edge consists of these two. So that one, of course, you could connect with a line, but since you're on this sort of representation, you just keep it like this. A loop, then, of course, would look like this, right? Then maybe you have like these three, right, taken all together. Of course, there's nothing stopping you from even taking like 4 vertices together. This would be like E5. So this is already like, this looks like a very different object here. What would you call this? This is a hypergraph. Okay, and lastly, there are infinite graphs. So if V or E are infinite sets, we obtain an infinite graph. Again, even if you think that maybe these are a little bit more exotic structures, and they are in a sense, but there's never something so esoteric that doesn't have some application somewhere. In fact, infinite graphs are actually, this is the topic of chapter 3. So we will discuss these things, time permitting, later in the course. Okay. So yeah, anyway, this is just kind of nailing down, what sorts of objects you can consider if you loosen or change some of these requirements. We are going to focus on finite simple graphs. So these are graphs without loops or multiple edges, and they're finite. So we will focus on finite simple graphs. Again, if you know anything about if you've taken an abstract algebra course, you know anything about group theory, you might notice the terminology here shared with group theory, finite simple groups. But we are going to focus on finite simple graphs. So these are finite graphs, first of all, and they have no loops or multi-edges. Okay, so that is what we focus on. Now, on to a big list of definitions. Again, if anything is unclear here, you can post your questions in the chat. So here is long list of terminology, notation, and uh, basically just like a long list of terms that you are going to see repeated very, very often in this course throughout the remainder of the course, so long as we're talking about graphs. So let's say I have a graph G. If there's no possibility for confusion, if we're not talking about multiple graphs, or we're not referring to some, if we're not referring to some other graph, we just have a single graph in front of us, we might talk about the vertex set as simply V, as I wrote before in the definition of a graph. But when there is possibility for confusion here, we would write V of G in this way. This is the vertex set of G. Similarly, E of G is the edge set. Of G. When we think about an edge, so an edge of G, maybe it is written as some pair of vertices. Maybe I've labeled those vertices U and V. Maybe I've labeled them 1 and 2, whatever. However I have labeled these vertices, writing them like this is kind of annoying, and now you see why also we might prefer to use letters here rather than numbers, because transposing letters is a lot easier to see in our brains than transposing numbers because of how our number system works. So typically the way that we would write this edge, just to save us on writing these stupid squiggle brackets all the time, or any other kind of bracket or whatever denotation thing we want to do, just transposing them is the most convenient thing. So just writing the two vertices in this fashion. This would even work in a directed graph if you took the this is like writing a vector, right? In like Calc 3, if you're writing a vector between points, you have initial point, terminal point, so you could even do that with a directed graph. But anyway, transposing them like this is fine. In fact, this is probably the most convenient way to write these things. The order of G, so the order of a graph G is the cardinality of its vertex set. You might say, why don't you just say size? You'll see why I don't just say size. So it's the cardinality of its vertex set. The size of G is the cardinality of its edge set. Okay. When two vertices, so given two vertices U and V in the vertex set of G, if the edge UV is in the edge set of G, we say those vertices are adjacent. Right? Again, you're putting in your brain, it does not matter, like notions of distance on the paper you're writing on means absolutely nothing. It's simply a question of are they connected by an edge or not. Of course, again, justify in your brain that not every possible edge belongs to the edge set. There are graphs where that is true, and we will talk about those graphs. Those are special cases, but of course, even going back to our very first example, for instance, there is no edge in the edge set connecting the vertices A and C. Right? That edge simply does not exist. So given vertices A and C, the edge AC is not in the edge set. It's not an edge, right? AC is not in the edge set here for this graph. So of course those are not adjacent in that graph. Okay. So that is that's the definition of adjacency for two vertices. Um, in this case, we say that U and V are the end vertices of the edge UV. So we say U and V are the end vertices of the edge UV. So again, this is just another way of describing it. Sometimes you want to state a theorem or a fact in terms of the end vertices, some edge. Sometimes you want to focus on the edge itself. This terminology is just giving us a way to do all those things. If an edge, or I should say, if the edge connecting UV is not in the edge set, right? So it's not an edge on the graph. Seems strange seeing if the edge is not an edge. But if UV is not in the edge set, or G, we would say that U and V are non-adjacent. Okay. All right. Just another way of describing adjacency and the relationships here that's going to allow us to define neighborhood here in a second. I'm going to say if an edge E, so I've just labeled the edge with a single letter. Don't be shocked or horrified. If an edge E has a vertex V as an end vertex, we say that V is incident with E. And all of this is just nailing down our terminology. None of this is too confusing. This is intuitive terminology that you yourself would have, if you were developing this subject, would have probably used something very similar to all of these things. But it's okay. Some of the stuff we're going to talk about, it's all right if you don't immediately have this seared into your brain, because it takes some practice of, reading problems, reading questions people ask you about graphs before you see exactly how this works. The neighborhood, it might be more precise to call this the open neighborhood, although in a context where I clearly don't care about a closed neighborhood, I might just slip and say neighborhood. Whenever there's not a word before neighborhood, it's assumed to be open. But more properly, maybe we should say the open neighborhood. This is not simply a convention in graph theory. This is also a convention in topology. It's not too crazy to see the parallels in the fact that these subjects are related. So the neighborhood or open neighborhood of a vertex V is the following. So this is the notation I'm using. I'm going to use this notation here to say this isn't anything special. This is just saying I'm defining this symbol to be what I'm about to write on the right. Okay, so this isn't a special equal sign or whatever. It's just me conveniently saying this is the definition of this thing. So this is the set of all vertices in the vertex set for G such that the edge Vx is in the edge set. What is this in words? right? So here's the set builder notation for this. What is this? It is the set of all vertices adjacent to V. Okay, had to reset my headset again. Okay, so moving on then. Well, if there's an open neighborhood, it makes sense to ask what's the closed neighborhood. So the closed neighborhood of a vertex V is the following. It is written with a closed bracket instead of open parentheses here. All this is the vertex V itself union with its open neighborhood. God, I did not mean to write that equal sign. There we go. So what is this? This is the open neighborhood, so it's all of the vertices that are adjacent to V and V itself, together with V itself, right? So it's all of the vertices adjacent to V along with V. Okay, so V and everything that is adjacent to it. Okay, given a set of vertices we'll say S, so S could be some subset of the vertex set of G. We could talk about the neighborhood of S. It's just going to be the union of the neighborhoods of vertices in S. So neighborhood of S is the union of neighborhoods. These are the open neighborhoods of the vertices in S. So if you wanted to actually write that, the neighborhood of S is going to be the union over all vertices X in S of the open neighborhoods. Okay. To get the closed neighborhood, it's going to be S union the open neighborhood. So the closed neighborhood of S you could write it again with a bracket if you wanted to. This is just going to be S union the open neighborhood of S. So that all of this nicely fits together in a coherent and consistent way, right? So we have consistency across all levels here. Okay. Next, the degree of a vertex. So we write this as degree of V, much like you would write degree of some polynomial here. What is this? This is the number of edges incident with V. And instantly, of course, it becomes clear where enumeration is useful when dealing with graphs. So we are going to see a lot of overlap, obviously, as this course goes on. Course with a textbook that's titled Combinatorics and Graph Theory. You're not going to get away from counting things, right? So The degree of a vertex is the number of edges incident with V, or incident with that vertex. Since we're talking about simple graphs here, so we don't have loops or multi-edges or anything like that, this is just the cardinality of the open neighborhood of V, right? So note, in simple graphs, this is the cardinality of, wrote an S there. It's the cardinality of the open neighborhood of V. Okay. Now, associated with degree, we have the concept of a max and min degree here. So the maximum degree of a graph G so the maximum degree of G is, we use capital delta here. It is defined to be, again, I'm going to use this symbol just to show that it's defined to be. You're not expected to know that this is not something that comes from anywhere else. So it is simply the max of the set consisting of the degrees of all of the vertices in G. So it is the maximum of all of the degrees of V. Similarly, the minimum degree we will use lowercase delta here. It is the minimum of that very same set. This might get you to thinking instantly, right? So whenever you're taking the max or min of a set, you might get a little nervous instantly because you might have flashbacks to Math 410 or real analysis where talking about infimums and supremums and maxima and minima, that's a little, that can be a little dicey here. But we don't have to fret because we're in finite land, right? We're in finite and discrete land, so it's not so scary here to think about these things because we can actually just list out, right? These are finite graphs, so we could list out every single degree for every single vertex, right? And of course, that's not so bad if you've got 10 or 20 vertices. That's not so annoying. But when you've got 65,537 vertices, that's more annoying, although of course it can still be done. But thinking more for the types of examples we've seen today, even in terms of graphs, we could just simply list out how this goes. So, for instance, let's go back, way back, very first graph I drew, this thing. If I wanted to actually just list out the degrees here, right? I could start with A and just go like this, like I can see the degree of A. Okay, there's 2 vertices incident with A, so that would be 2. And then B, there are 3. And then D, there are also 2. And C, there's 1. Okay, so that's fine. Now, this sequence that I've written out, I organized it in this way because A, B, C, D. But that's kind of a silly way of doing it because I could have labeled these however I wanted to. There's nothing stopping me from labeling this one A and this one B and this C and this D, or changing this up. So when I'm talking about the degrees, it makes more sense from a organizational standpoint to have some kind of ordering on this So ascending or descending. The convention is typically descending order. So this sequence I would write instead as 3, 2, 2, 1. That way, the actual ordering, A, B, C, D, I could just delete that. I could take those away, and you could still understand that, okay, there's a vertex that has degree 3. There it is. There's two vertices that have degree 2. There they are. And then there's a vertex that has degree 1, and there it is. Okay. This sequence of the degrees associated to each vertex, this is called the degree sequence. Okay, so this is the degree sequence of a graph of order n is just an n-term sequence written in descending order, usually, of the vertex degrees. Of course, there's nothing saying it has to be written in descending order, but that is the that is an easy convention you could adopt to save yourself a lot of hassle. So the degree sequence of a graph of order n is the n-term sequence containing the degrees of all the vertices. Okay. Now, this is nice. So let's actually here. I'm going to go back and use this graph to talk about some of these things. So let's go back to our first graph here. Right. There it is. So what is the neighborhood of, say, what is the neighborhood of A here? The open neighborhood of A. This consists of the vertices that are adjacent to A. So this would be B and D. Those are the two vertices adjacent to A. What is the closed neighborhood of A? This would be the vertices adjacent to A and A itself. Okay. What is the maximum degree of the graph G? Well, there's its degree sequence, so 3. What's its minimum degree? Again, there's its degree sequence, so 1. You see why, if you are interested in writing out the maximum degree of a graph or the minimum degree of a graph, looking at its degree sequence in either ascending or descending order, whichever, is nice because it's just either the first or last term in the sequence tell you these things immediately, rather than you having to hunt through the list, right? So anyway, that's another reason why you'd want to do this. And of course, the degree sequence, as we wrote, is 3, 2, 2, 1 here. Okay. All right. So that's this is our example of illustrating those things. All right. So let's actually prove kind of the first thing we've proved in this course so far. You might, when you were looking at the course, thinking about signing up for the course, you might have wondered how much proof is going to go on in this course. There will be some proof. It's not going to be it's not going to be like Math 410 levels of proof. The proof is going to, I mean, well, what does that even mean, right? A proof is a proof. But what I mean by that is that there's going to be a lot of proof by picture or by example, and much of the proofs are very intuitive in a way that you can't exactly replicate in, say, a real analysis course. But no, you will be asked to prove things. But don't worry too much about it. You don't need to stress out over it. So here's an example. This textbook calls it the first theorem of graph theory. So I will follow suit. which is that the second we start writing out a degree sequence for a graph, instantly you are thinking in your head, and we're going to address these things eventually, but you're instantly thinking in your head, oh, if I have two graphs in front of me and they're like unlabeled and someone asks me, are these the same graph or are they related somehow? One thing that might help me is knowing the degree sequence of both of the graphs, and then maybe I could compare them and see, do they have the same number of vertices that have the right degrees, or are there some that don't match? You might think to yourself, why does that matter? But intuitively, I think you understand that that has something to do with kind of classifying the graph, or at least classifying certain properties that the graph could have. For instance, knowing that the minimum degree here is 1 instead of something else, right? Could definitely tell you something about how the graph behaves. So in this case, what does this theorem concern itself with? So in a graph, in a graph G, the sum of the degrees of the vertices is equal to twice the number of edges. So the sum of the degrees of all the vertices is equal to twice the number of edges. Again, you might have actually noticed this is the case before I even wrote this down. Consequently, the number of edges with odd degree is even. Okay. Well, how does this work? Why is this true? So first of all, we'll say let S be equal to the sum of all of the degrees. So the sum over the vertices in the vertex set for G of all of the degrees of the vertices. Now, I don't have to draw you a picture of a graph, but here, maybe I'll just put one in front. Let's just use the same one. As I go from vertex to vertex, right? So when I'm looking at the degree of A, that's 2. When I get here, this is 3. But let's consider where that 3 comes from. One of the edges making up that 3 is an edge I have already counted when I counted A. I counted this top edge. In fact, do I have different colored pen? I think I do somewhere, maybe. Maybe not. Nope, can't find it. Okay, that's fine. So I counted this top edge once when I counted for A, and then I counted this edge from A to D once, again counting the 2 from A. B, I have now counted the top edge again. I've counted this BC edge once, and I've counted this BD edge once. Okay. So that's me summing 2 and 3. So 2 plus 3, I'm keeping track of the edges I've counted. And the marks are the number, or the total, right? So I should have 5 marks. 1, 2, 3, 4, 5. Yep. Okay. I get to B. This is what I got. When I get to D, I'm counting this edge again. And then I'm counting this edge again. I've already counted it when I counted A. So that's the sum 2 plus 3 plus 2. And then when I count the edge, the single edge that that emanates from C, here that completes everything I did here. Notice every single edge was counted exactly twice. It was counted when you counted the first vertex, and then the whatever edge you counted emanating from that first vertex when you counted the degrees of another vertex that was adjacent to it, you counted that edge again. But you didn't count more than that, so you just simply double counted everything, right? So you double counted every single edge. So in that way, right, the fact that this graph is this small or looks like this, that is not going to change. The way that this is going to work is exactly that you are going to double count. And so what this means necessarily is that what this is just 2 times the number of edges. Now, it looks like I've just argued from nothing, but those words I just said are the reason why, right? So this is, we double count each edge. So we double count each edge when we sum the degrees. Okay? But this means that S is even. That is, the sum of the degrees is even. So then this second thing, the number of edges with the odd degree is even, that follows because if the number of edges with odd degree was odd, S would be odd. But it's not, it's even. So this implies that the number of edges with odd degree is even. So not too much to prove there. This is literally just tracking through what happens when you sum those degrees. Necessarily, you're double counting all the edges, so it's 2 times the number of edges. Because that's an even number, you would have the even degree and odd degree. Those have to combine, those have to sum to produce an even number. So the number of odd degree has to also be even, because if it was odd, it would produce an odd number, but it doesn't. So that's it. That's the end. And so that is our first theorem. This is this is something telling you of the relationship that these degrees have with or summing all the degrees, what that corresponds to. You're essentially double counting the edges here. So okay, now to move on to another part of this that closely is related to some, if you've had Math 432 or you know anything a little bit about topology, you're going to understand the next, how this relates rather, when we talk about connectivity. But that's not the angle that we're going to be talking about in this course at all. We're going to have much different concerns. But this is, should I draw the picture first or should I say the thing first? I'm not going to draw the picture yet. I'll do that in one big example after I'm done. So this is going to be more shotgun approach with a bunch of definitions. Okay, so a walk in a graph G is a sequence of not necessarily distinct so put that in parentheses, not necessarily distinct vertices V1, V2, and so on, stopping at some, say, VK. Okay, such that each edge, VI plus 1, is in the edge set of G for each I. Goes up to k minus 1 because the stopping point is k. All right, v sub k. Okay. To wrap all of this notation into maybe uh, a single thing, you might call this a v1 to vk walk. So call this a v1 to vk walk. If you wanted to go ahead and include the vertice notation that you are going to be using here, so you might see it called that. In either cases, we'd say that v1 and vk are the end vertices of the walk. Let's again go back to an example we've beaten half to death now. The first graph I drew. I'm going to draw a better, bigger example here when we talk about these other things here in a second, but I'm just going to use this for now. So for instance, what would a potential walk be like here? Maybe my walk is A, D, I'm just going to do it like this. I'm going to say A, D, B, C, B, A, B, D. So the walk terminology is intuitive, of course, because if you think about this denoting some kind of like, I'm trying to avoid using certain words here because they're going to have specific meaning. But if you imagine this being, we'll say a path for now, but then that word is going to be forbidden from this context, except in a very specific way here in a second. But if you imagine me walking along the trajectory, well, yeah, we'll say trajectory, indicated by this. This is like A, D, B, C, B, A, B, D. So I was doing that to show that in each case, the edges required to be in the edge set were there. There's no DC, right? I can't, if I put a C here, that's not allowed as a walk because there is no edge that takes me from D to C, right? So they're not connected. DC is not an edge in this graph, so that wouldn't be allowed. But this is allowed, so all of those edges were in the edge set. And this is allowed. And of course, there are repetitions here, right? A repeats, B repeats, D repeats. So there are repetitions here allowed. That is what a walk is in a graph. Okay? But then instantly, of course, you have some questions about this. So you ask yourself some things like, oh, I should say one more thing before I say that. Notice that the walk consists of the vertices. It makes reference to the edges, but the edges are not like a part of the walk. They're just required to be there. It's the vertices that make up the walk. Of course, the vertices have to be vertices that all have edges between them as you're going, along the walk. Okay, but then immediately, like I said, you're going to have certain things you maybe try to impose on a walk. You're going to say like, oh, what if I don't allow repetitions? Right? What if I just don't allow repetitions? That's one immediate thing you could say. So if the vertices are distinct, that is going to have a different name. So if the vertices in a walk are distinct, then the walk is called a path. Okay. Now, I'm going to say something else that is not going to be super Well, I mean, it might be obvious, but it's going to be something that is a little bit confusing until you really sear it into your brain what these words mean, because of course these are English words that you use in other contexts, so it's hard to nail them down in the same way you nail down vector space, right? So then the walk's called a path. So in the example that I did before, this would not be a path because the vertices are not distinct. But for instance, if we stopped like here, if we just stopped at C, all these vertices are distinct. So A, D, B, C, that would consist of a path. So this whole thing is not a path because it has repetitions, but this subwalk here, right, actually is a path. That'll come into play with the next theorem that we prove, but for now, let's do more on this notation, or this terminology rather. Okay, if the edges in a walk are distinct, then the walk is called a trail. Hmm. Let's think for a second. If the vertices in a walk are distinct, then the edges in the walk have to also be distinct, right? There's no way you could have repeating edges if you don't have repeating vertices, right? And you can do that. Here's the proof of that, right? You say, well, what would it mean for an edge to repeat? It would say, you both of the letters would have to show up, right? So if your edge is UV, U and V both have to show up twice. But if U and V show up twice as edges, they're going to show up. There's going to be repetition amongst U and V as vertices. So every path has to be a trail. Note, this means every path is a trail. But not every trail is a path. And the way to see this is, again, because the fundamental feature of defining both a walk and a path has to do with the vertices. That's what it's focused on, is the vertices. Yes, the vertices have to be those that correspond to edges that are in the edge set, but it's the vertices that are being focused on and the vertices being distinct, whereas trail only references the edges being distinct. So what is easy example showing this? Here. Here's let's take a graph of order 5. There, right? This hourglass looking thing. And let's label this. We'll say A, B, C, D, E. We don't have to label these. You can see what it is that's going on here. All right, so notice that A, B, C, D, E, C, A is, what is that? Let's follow it. Well, that's a walk. It's a walk where all of the edges are distinct, so it is a trail, but not a path. You might say, well, this last one, maybe there's some way we can get around that by just including the last edge. But this C repeats itself, right? So there's no fixing this. Like this is a trail that is not a path. That's it. Um, so every path has to be a trail necessarily, but not every trail is a path. Just something to think about to help your intuition for this sort of thing. Okay. And so let's do a couple more things, and then I'm going to draw a nice picture, and we're going to discuss these things. So I want to talk about a closed path or a cycle. So a closed path or a cycle, as it's called, is a path v1 to vk. Again, notice that now necessarily these every v sub I is distinct here because this is a path. Um, I'm going to write this here, and then I want you to think about why this is the case. K must be bigger than or equal to 3 here. And think about why that is. Remember, finite simple graphs are what we're talking about. So you can think about why for a path, you have to have at least 3 vertices here for a closed path in this way. Well, I haven't written the last part of this yet, so me writing this right now, you're going to say that's not true. You could have a path that's not at least 3. But you will see why this has to be the case for what I'm about to write. So maybe that was a little confusing. But so this is a path together with the edge vk v1. So that in this way, it is a closed path because this closes up. So, for instance, an example of a cycle in this graph would be ABC. So I have ABC taken together with the edge CA. This is a cycle. Now, you could say, wait, this taken together with business, that sounds almost like cheating. It's to show you that this allows our terminology to work the way that it does because it allows us to say that the vertices are still distinct, A, B, C. These are connected by an edge, but I don't want to put A here because then that screws up my definition of path, right? My definition of path would have to be much more annoying to make that work. So this is why we do this together with this edge. And that's what I was referring to here when I said, oh, you might think you can fix this by saying, oh yeah, just include that edge. But no, the C already repeats here, so there was no fixing this trail. Anyway, okay, so that's the definition of a cycle. Now you can think to yourself why this is needed in the types of graphs we're talking about, why this has to be the case. You could try drawing something that violates this and see where that gets you. But similarly, a trail that begins and ends at the same vertex since trail is referring to the edges anyway, this is called a closed trail or a circuit. We'll use all of those terms. Sometimes I'll call it a closed path, sometimes a cycle, sometimes I'll call it a closed trail, sometimes a circuit. So that's why everything is included here. That won't be too confusing. The length of a walk, path, trail, cycle, circuit, whatever you want to call it, is its number of edges counting repetitions. So the length of a walk, all of these are walks, so I could just stop there, but just to emphasize here, path, trail, cycle, circuit is its number of edges. Counting repetitions. Hmm. Failing spelling class here. Okay. So let us draw a nice graph and talk about some of these terminology or some of these terms that I've given here. So let me make it big enough to see everything that's going on here. So let's label these. Let's say A, B, C, D, uh, E, F, G. Let's have. Mm, is that everything I want there? I think it is. Okay, so let's consider this graph, G. So let's look at ACFCBD. So ACFCBD. First of all, I know it's not a path because C repeats here. So let's trace this out here. A, C, F, C, B, D. Okay, what is the length here? 1, 2, 3, 4, 5. So this is a walk of length 5. Okay. What about BACBD? Now, BACBD, what could I say about that? BACBD. Because of the repetition of B here, this isn't a path either. Even though a trail only refers to the edges, so technically what we're using here is just, this is a sequence that refers to some edges. Those edges were distinct. So even with the repetition of B here, the edges were distinct. So look, B, A, C, B, D. Those edges are distinct. That is so this is actually a trail of length 4. Okay. What about DGB A, C, F, E. Looking at this, there are no repetitions among the vertices. Let's see that all of these edges, though, are actually there, right? Because the thing is that all of the graphs here that I've shown so far are an example of what I would say is connected, what we're going to call connected in this course. But we see actually that, like, there's nothing preventing me from having some vertex off here that's not connected to anything, right? That's 100% allowed. We're going to see examples of that. We're going to talk about connectivity of graphs very soon. That's where we're headed after we talk about this next upcoming theorem. But this is the idea here. Anyway, I have to make sure, even if you have a graph that's connected, not every vertex is connected to every other vertex. If the second vertex here was C, if this was DC and then something, well, D and C are not connected, so that's not allowed here, right? That would not represent anything. But here, tracing along, we're going to see that this sequence actually represents something. Let's see what that something is. D, G, B, A, C, F, E. Every edge indicated is an edge in the edge set for this graph. So this is fine as a walk. It is also a path because there are no repeating vertices, which makes it a trail as well. So this is a path of length 6. Again, every path is a trail, so it's also a trail of length 6. Okay. Let's see some other things going on here. So about G, D, B, C, A, B, G. G, D, B, C, A, B, G. G, D, B, C, A, B, G. It is not a path, but it is a trail. It is a trail that begins and ends at the same point. It's a trail, of course, because none of those edges were repeating, right? They're repeating vertices. It even starts and begins at the same vertex here. But all of those edges were distinct. So this is a trail that begins and ends at the same vertex. So it is a circuit. Let's look at E, D, B, A, C, F, E. Now, again, you may look at this and say, well, there's repetition of the E, so it can't be a path. But that's because the only repetition that happens is at the end. This is a little different. Because I could say, no, that's not there, and I consider this path, which has no repetition, taken together with the edge FE. So when I write something like this, and I'm going to say very quickly, this is a path, it's a cycle, actually. What I'm doing is saying, well, the cycle in question is actually this thing, EDBACF, taken together with the edge FE. But writing it this way hopefully doesn't ruffle any feathers here because you think that I'm going back on my definition that there can be no repetitions. That's not what I'm doing. I'm just saying that this is more convenient than writing EDBACF together with FE. That's all I'm saying. Okay, but now that we have done that, I'm going to do this throughout the semester. So hopefully this doesn't cause any confusion. So there is no repetition here because of how we've defined cycles. Okay, so this is a circuit and this is a cycle. So note, walks, paths, trails can have length 0, but the least possible length of a cycle or circuit is 3. You might say, oh, well, you just put that in the definition, right? When you wrote that k has to be bigger than or equal to 3 on the previous page, when you wrote k has to be bigger than or equal to 3, you included that in the definition. So you're just defining it that way. No, not really, right? That is forced on us. And that's why I'm saying draw some examples on your own to see why that's forced on us for finite simple graphs. Okay. So that's the idea here. That the least possible length of a cycle or a circuit or cycle is 3. Okay. Now, before I state the next theorem, I'm going to go back again to our very first example. And I gave you an example of a walk, right? When I first defined a walk, I gave you this example, ADBC, BABD. And I said, well, clearly that's not a path. Once I defined path, I said it's not a path because there's repetition of many vertices here, right? But I identified that there was actually a path inside this walk. So, and of course you could say, well, of course you could, I mean, saying that there's a path inside this walk that's not super interesting because of course you could just literally take AD is a path. So then the question is, well, but is there a path to a given, so if I have a walk, we'll say like an AB walk here, right? So this, if I stopped here, this would be an AB walk. And you could say, could you find an AB path in this AB walk? And you could. There it is. I need to cut out that C here, but there is my AB path in my AB walk. I cut out the extra stuff that had repetitions I wasn't interested in, and I got a path from A to B within this walk. It's like a subwalk of this thing. And the question is, can you always do this? And the answer is called the second theorem of graph theory, and the answer is yes, you can. So, theorem, this is second theory, or second theorem of graph theory. So, in a graph with vertices u and v, we'll say in a graph G with vertices u and v, every UV walk contains a UV path. Now, you might already be thinking about how you would kind of like algorithmically pick this. You could call it a more efficient, right, walk, right? It's more efficient thing than the UV walk, because you think to yourself, if something is a UV walk that's not a UV path, in some way that means there's some extraneous stuff that you're doing. There's some repetitions that occur that are unnecessary if your sole goal is moving from U to V, right, along edges. So if your sole goal is moving along U to, or moving from U to V along edges, a UV path is a more efficient object than a UV walk, just a generic UV walk. So the fact that you can always throw out this extraneous stuff to make this more efficient is nice. The question is, how do I do this in general? So we'll prove this, and then that will be all for today. So how do I go about this? So let W be a UV walk in the graph G. So the idea is to induct on the length of the walk W. So we wish to use induction on the length of W. Of course, doing a proof by induction shouldn't be too big of an ask for you all. Whether you're math or CS, you've been suitably beaten over the head with induction many, many times by now, so hopefully it's forever ingrained. You could be woken up in the middle of the night screaming and asked to prove something by induction. And if it's not, it's one of the standard proving some closed form formula for a sum or product or something, you could likely do that half asleep. Here, maybe the main thing is just seeing that what we're inducting on is the length of the walk. Of course, if we consider as our base cases even, you could think of a length 1 or length 2 walk. For length 1 or 2, 1 or W, 1 or 2, W must be a path already. And that's just by definition of path. If it's length 1 or 2, there's no repetitions to be had there. It must be a path, so there's nothing else to say. So our base case is true by definition. We love that. So now we have our inductive step, our inductive hypothesis. So for inductive step, say that the result is true for walks of length less than k, and suppose W has length k. So we'll say it's true for walks of length less than k, and say that W has length k. Now, it could be that W is already a path, right? A walk can just be a path. So if W is already a path, we're done and there's nothing to do. But let's see what W consists of in order to be done here. So I'm going to move on to the next page, give myself some room here. So say W is the walk that looks like this. So we'll say that its first vertex is W naught, which is U, since it has to be a UV walk, and then W1 and W2 and so on out to W k minus 1 and WK, which necessarily has to be V since it's a UV walk. Okay, where vertices are not necessarily distinct. right, where the W sub I are not necessarily distinct. Now, of course, if they are distinct, we're done. Okay, so if they are distinct, we're done. Why are we done? Our desire was to find a UV path. If the UV walk we started with was already a UV path, then of course it contains a UV path. It is itself a UV path, so we are done. Okay, so that's that. So then we must suppose, right, that we're in the other case where these are not all distinct. There exists one that is repeated somewhere. So if not, let J be the smallest index, right, the smallest integer such that we have Wj is equal to Wr for some r that is between 1 and k, right? But we'll say for some r bigger than j but less than or equal. So what are we going to do here? Well, the idea is let's think about it like this. Like, so I'm kind of doing it backwards here because what I'm about to write is what you would do after you thought about how to do this. So what is the idea? The idea is if there's a repetition, right? There might be multiple repetitions, right? It doesn't matter. Pick like pick the smallest integer or the smallest index that is like the first repetition here. So let's think for a second. The idea is that I have a repetition. Well, past some point, right, in that repetition, like I could just start from the last place it was equal to this W sub R, right? So basically, wherever this repetition is, if I delete that repetition of that next appearance of W sub R and replace it with what comes later, I have shortened the walk, but I still have a UV walk. The fact that I've shortened it is the important thing, though, because I have the inductive hypothesis telling me that if my walk is any shorter than W, the result is true. And so I will have found the path that I wanted. Okay, and what's even better about this is unlike what happens in a lot of inductive proofs, this is kind of sort of hopefully telling you maybe how you would even go about doing this. Like if you were to actually practically set about finding this is maybe telling you something you could do, but maybe not. We'll think about that, right? We can do this with a few concrete examples. So, but that's just something for you to think about. Okay. So, what do I want to do here? Consider the walk W1, which is, it begins at U, and it proceeds all the way up to this W sub j. And then because we know that W sub j is the first time there's a repetition of a later W, we just cut it and paste the walk from that W on. Right? So now we have deleted WR. We know that WJ is equal to WR. And we've started now at W sub R plus 1, R plus 2, all the way to K, which is still V. So of course what we did was shorten this walk. So notice the length of W1 is less than K. So the inductive hypothesis applies. Thus, W1 contains a UV path. But since W1 contains a UV path, W contains a UV path, since W1 is just a subwalk of W, if you like. And that is what we're proving. Now, again, I would like you to think about whether or not this inductive proof, and induction is famous for not actually telling you what's going on, kind of. Right? Or as the joke goes, to do a proof by induction, you have to already know the answer. But I want you to think about whether or not this helps you at all actually constructing the UV path. Maybe it does, maybe it doesn't. Don't know. You're going to have to think about that one. So anyway, that is, I think, a good stopping point for this first lecture. Like I said, the remaining lectures this week will be about 20 minutes longer, about like this one was. And that's that. We'll continue on here. What we did here is kind of superficially similar to the next thing I want to talk about, which is the notion of deleting a vertex or deleting an edge from a graph, doing some kind of modification operation on a graph itself. It's the first place we'll start for tomorrow's lecture. I'll be making announcements about other things like plans that I have for additional office hours, homework, things like that. I'll be talking about that soon, so keep a lookout. But otherwise, I will see you tomorrow at 11. So yeah, I'll see you then. As always, if there's any kind of audio issues or any other issues with can't see, there's some non-clarity here because this is brand new camera, so it doesn't have the same settings as my other one that I'd been using for 5 years. So you're just gonna have to let me know about that in the chat, and I will fix it. And that's that. So anyway, I will see you all tomorrow.